This video is on section 6.3 notes, sum and difference identities. So the identities are listed up here for you. They are also on the resource page that I created that you should have printed with your section 6.2 notes. So you can use them either from these notes or from the resource page. And in these notes, we're going to go through how to use these formulas to evaluate some different angle measurements using the unit circle. And then after that, we're going to go through and we're going to use some of these identities that show up in proofs. So first, if we look at this, this is an angle that you might not recognize because it's not on the unit circle and it's not coterminal with an angle that's on the unit circle. So what I'm going to do first, because I'm not great with fractions, adding fractions or subtracting them in my head, is I'm going to convert this into degrees. So this is 195 degrees. And then I'm going to look at the unit circle to see what angles could be added together or what angles could be subtracted to create that 195 degree angle. So whenever you do these problems, there's always multiple approaches you could take. And the answers might look slightly different. They would equal the same decimal approximation, but they might look slightly different depending on which approach you take. So if I look here, if I'm trying to create 195, I could do like 150 plus 45 degrees. So I'm just going to write down what some of my options are. 150 plus 45. I could do 135 plus 60. I could do 225 minus 30. I could do 240 minus 45. And so on. There's other options I could do as well. So I just want you guys to know that as you come up with different potential ways to do this problem, there's always going to be more than one. And you could use your addition formula, you could use your subtraction formula, and you'll notice they're nearly identical anyway. Okay, so I'm going to go ahead and just do the first one. So I'm going to do cos of 150 degrees plus 45 degrees. And it doesn't really matter at this point if you use the degree version or if you use the radian version, as long as you're looking in the correct spot on your unit circle. So I'm going to use the radians just because that is my comfort zone. I'm so used to doing everything in radians. After you've done a lot of the upper level math classes, they ditch degrees completely and they just do everything in radians. And so whichever you are more comfortable with is how you can write it down, and that's fine by me. Okay, so I'm going to go ahead and copy the formula now. So I'm adding the two degree measures together, 150 and 45, and so alpha is the first angle measurement, the 5 pi 6th, and then beta is going to be the second one. So this is going to give me cos alpha times cos beta minus sine alpha times sine beta. All right, so cos alpha is negative root 3 over 2. Cos beta is root 2 over 2. Minus sine, it's 1/2. And root 2 over 2. All right, so when we multiply fractions, we just make sure that we multiply the numerators together and multiply the denominators together. And when we multiply square roots, we just make sure that we multiply the number underneath the square root. So root 3 times root 2 is root 6, negative root 6. 2 times 2 is 4. subtract 1 and root 2. If you ever have a number that is not under a square root, that would be multiplied by the number in front of the square root. So there's like an imaginary 1 here that's just not showing up. 1 times 1 is 1, and then there is no number under the radical, so this is just root 2. So you could say this one and the one in front of the root 2 multiplied to be a 1 right here, and you just didn't have to write it. And then 2 times 2 is 4. And then you can write that as one fraction with a common denominator of 4, and you get negative root 6 minus root 2 over 4. And we can check our answers on all of these. I can make sure that I'm in radians because the original problem was in radians. And I can type cos 13 pi 12ths and get my decimal answer. And then I can type in negative square root 6 minus square root 2 divided by 4. And I can see that my decimal answers are identical. So I know that I did that correctly. All right, next, sine 23 pi 12ths. So 23 twelfths in degrees is 345 degrees. So again, I have a few different ways that I could create this. I could do 300 degrees plus 45 degrees. I could do 360 degrees. I had written on my paper 360 minus 15, which does equal 345, but I don't have a 15-degree angle on my unit circle. So I could do 390 minus 45. 390 would just be a coterminal angle. I could do that. Anyway, I'll go ahead and I'll just do the first one here. So I'm going to do sine of 300 plus 45. And 300 is 5 pi thirds. And 45 is pi fourths. And you can see that the tangent formula is quite a bit different, but the sine and cosine formulas are very similar. So these are going to feel somewhat similar as you do them, and their answers are going to look somewhat similar as well. So for sine and for addition, we have sine of the first angle, cos of the second angle. So sine 5 pi thirds, cos pi fourths, plus, and then cos of the first angle, sine of the second angle. Cos 5 pi thirds, sine pi fourths. Okay, so sine of 5 pi thirds is negative root 3 over 2. Cos of pi fourths is root 2 over 2. Cos of 5 pi thirds is 1/2, and sine of pi fourths is root 2 over 2. So the numbers are very similar to the previous problem. We get negative root 6 over 4 plus root 2 over 4, so that's a little bit different. Negative root 6 plus root 2 over the common denominator. And again, we can check this out. We can do sine of 23 pi twelfths and just make sure that that decimal is negative square root 6 plus square root 2 over 4. And it is. Okay, so you'll notice that when you do sine and cosine, the answers tend to be similar, which makes sense because you're coming up with values from the unit circle, and cos and sine are the x and y coordinates, and those are always similar. So next we have tangent, 5 pi 12ths. So again, I'm going to put that into the calculator. And this time we're working with 75 degrees. And so I have a few options here as well. With 75 degrees, I could do 45 plus 30. I could do 120 minus 45. I could do 135 minus 60. And with tan, we actually have a little bit of strategy involved. And the strategy that's involved is that we want to specifically work with tangent where the ratios that we're going to use are going to be a little bit easier. And I want you to think about the way that this formula works for tan, because we have tan on the top of a fraction and tan on the bottom of a fraction. And we know that values for tan could be 1, if you have root 2 over 2 divided by root 2 over 2. So 1 would be really nice to plug in here. It could be root 3. Or negative root 3, and that's if we had an x coordinate that was 1/2 and a y coordinate that was root 3 over 2. Or we could have tan being root 3 over 3, and that would be if we have an x coordinate of root 3 over 2 and a y coordinate of 1/2. And if we had root 3 over 3 in the top and bottom of this fraction, that would suddenly become a much messier problem, because we would have a fraction on the top and a fraction on the bottom, and we would have to get common denominators, and we'd have to do a lot of work. I'm actually going to show you what would happen if we did that, but we are not going to do that. We are going to avoid that. So when you do the tangent problems, what you're going to do is you're going to come up with a few examples of ways that you could come up with that degree measure, and then you're going to look and you're going to manipulate the problem so that you can avoid any version that makes you use a root 3 over 3 in the problem. So if I use 45, that would be fine because tan is just 1. If I use a 30-degree angle, this is the tangent version that is root 3 over 3. So I am not going to do the first version. That version would be difficult. 120 and 45. So 120, this, if I do tangent y divided by x, that would be negative root 3. That would be pretty easy to work with. We already know that 45 is going to be pretty nice to work with, so this would be a good one to do. 135 would also work pretty well. I would have 135 would give me negative 1, and then 60 would give me a positive root 3. So that one would be nice as well. So you're going to come up with a version that is going to make your life easier when you do the math on it. So I'm going to go ahead and just do 120 and 45. I'm going to avoid 45 and 30 because I know that that one would be more difficult. So tan of 120 minus 45, and 120 is 2 pi thirds, 45 is pi fourths, and so when I write this out, I'm going to have tan of the first one minus tan of the second one divided by 1 plus tan of the first one times tan of the second one. Okay, so tan of 2 pi thirds is root 3 over 2 divided by negative 1/2, and I know from chapter 5 that that's just negative root 3. And at this point, you don't have to show all your work for those anymore. We've done this long enough that we just know the answers, and I'm not going to make you do all the steps. You're welcome. Tan pi fourths, root 2 over 2 divided by root 2 over 2 is just 1. 1 plus negative root 3 times 1. Okay. So what I end up with here is negative root 3 minus 1 over 1 minus root 3. All right, so this is really nice because I didn't end up with fractions on the top. I didn't end up with fractions on the bottom. I just have one fraction that is the problem. If I had done 45 and 30, I would have had fractions on the top and fractions on the bottom, and it would have added a whole extra step. Now, the part about tangent that students still don't typically like is that this denominator has a radical in it, which means that it has to be rationalized. So I need to multiply the top and the bottom by the conjugate. So I'm going to multiply by 1 plus root 3 on the top and 1 plus root 3 on the bottom. And what's going to happen when I do that is I'm going to get rid of my radical, and the bottom of the fraction is just going to be more proper without a radical in it. Okay, so I have to FOIL the top, I have to FOIL the bottom. So I'm going to put parentheses around these. Negative root 3 times positive 1 is negative root 3. Negative root 3 times positive root 3 is negative 3. So a root and a root cancel and you just get the number. Or you could think of it as root 3 times root 3 is root 9. Negative, the square root of 9 is just negative 3. All right, then I've got the negative 1 I need to multiply. So negative 1 times 1 is negative 1. Negative 1 times root 3 is negative root 3. Okay, and then on the bottom, 1 times 1 is 1. 1 times positive root 3 is positive root 3. Negative root 3 times 1 is negative root 3. Negative root 3 times positive root 3 is a negative 3. Okay, so on the top, I'm going to combine my regular numbers first, and then I'll combine my radicals. So negative 3 and negative 1 gives me negative 4. Negative 1 root 3 and another negative 1 root 3 gives me negative 2 root 3. And then on the bottom, the positive root 3 and the negative root 3 cancel, and I have a 1 and a negative 3 gives me negative 2. Now, this radical cannot cancel with anything, but I do have a whole number 4 that can be reduced, and I do have a coefficient of negative 2 that can be reduced. So if all 3 of these numbers can divide by the same thing, then I can reduce them. And all of these numbers can divide by negative 2. So negative 4 divided by negative 2 is positive 2. Negative 2 divided by negative 2 is positive 1. And then negative 2 divided by negative 2 is positive 1. So I am left with 2 plus 1 root 3 over 1, which is just 2 plus root 3. All right, and I want to show you, because I did the problem first with 45 and 30, and so if you did 45 and 30, this is how the problem would have started. You would have had fractions that you plugged in here and here, and when you have fractions, you have to get a common denominator to be able to add these terms together, so you would have had that. And then here's me getting the common denominator and writing them each as one fraction. And then because I had a fraction over a fraction, I had to take the bottom and flip it up and multiply by the reciprocal and reduce. And then this is what I ended up with as I was like, oh, that's my final answer. But oh no, I have a radical. And so I had to multiply by the conjugate. And then this is me doing the multiply by the conjugate, and I'm foiling my answers out, and this is what I got. And I still got to the same final answer, but I did a lot more work. And I did that work because I used 45 degrees and 30 degrees, and it was a little bit easier if I just used 120 and 45. So you'll get the right answer, but you're just going to work a little bit harder to get there. Okay, and then again, we can always check our work here. We can do tan 5 pi 12ths and make sure that 2 plus the square root of 3 is the same decimal, and it is. All right, now the next problem, sorry, hit the mic. The next problem is a different format, but still uses the same identities. So it says simplify the expression and write the exact value. And if we look here, we can see like, oh, this is kind of like they took some values and they plugged it into the formula. So we just have to figure out which formula they used. So cos and cos, sine and sine, it's not one of the sine formulas, It must be one of the cos formulas, cos and cos, sine and sine, but it has a plus sign in between. So it is a cos formula where two angles were subtracted. Alpha subtract beta, and cos alpha, cos beta. So they must have been subtracting 47 and 2. So this is the same as cos of 47 minus 2, which is cos 45, right? Because 47 minus 2 is 45. And I know what that is. Cos of 45 is just root 2 over 2. And I can check this on my unit circle if I want. I can just plug this in, or sorry, not my unit circle. I can check it in my calculator because I just did this on my unit circle. But I could plug this into my calculator and just make sure it's the same decimal. All right, for this one, we have a sine and a cos and a sine, and so that's not the cos formula. This would be the sine formulas. The one with the minus in the middle is the subtraction, and so the angles that they must have been subtracting is the first angle minus the second angle, alpha minus beta, and so the alpha is t and the beta is 2t. So this problem was sine of t minus 2t. T minus 2t is just negative 1t, or you could say negative t. And this is actually one of my even and odd identities. So I'm going to go ahead and get out my resource page. Sine of a negative angle is negative times sine of the angle. So this is negative sine of t. All right. So kind of weird problems, but there you go. Okay. And then, of course, we have to try these little triangle problems or Pythagorean identity problems. We did a couple of these, I don't know, 6.1, did we do some of these? Where I said you can draw triangles if you want, or if you wanted to, you could use the Pythagorean identity. So it says to find the exact value of sine alpha plus beta, given that sine alpha is negative 3/5 and cos beta is negative 1/3. Alpha is in quadrant 4 and beta is in quadrant 3. So first I'm going to find, I need to know what sine of alpha and beta are. I need to know what cos alpha and beta, and then I'm going to use the formula. So I'm going to go ahead and do everything to do with alpha first. So I'm going to use the Pythagorean identity. Like this, to find my missing ratio. So if I have sine alpha, I also need to have cos alpha, and they did not give me that in the problem. So sine alpha is negative 3/5. So that squared plus cos squared equals 1. Negative 3/5 squared would be 9/25. And so I'm going to take the 1, I'm going to subtract the 9/25 from it. And so that I can subtract these, I'm going to think of the 1 as 25/25. So cos squared alpha is 16/25. And then if I square root that, then I know that cos alpha is either positive or negative. I'm not sure yet. Square root of 16/25 would be 4/5. So I know the ratio is 4/5. I just have to think about if it would be positive or negative. So I'm just going to remember my signs. All students talk constantly. Alpha is in quadrant 4. And in quadrant 4, cos is positive. So cos alpha is positive 4/5. Okay, so I know sine alpha is negative 3/5, and cos alpha is positive 4/5. Now I'm going to go ahead and find the information for beta. So I'm going to do sine squared beta plus cos squared beta equals 1. Sine squared beta plus negative 1/3 squared equals 1. Negative 1/3 squared, negative 1/3 times negative 1/3 is positive 1/9. And I'm going to take the 1/9 and just subtract it over from the 1. And so the 1 I'm going to think of as 9/9. 9/9 minus 1/9. So sine squared is 8/9. And then I just need to square root both sides. So sine beta is plus minus the square root of 8 over 3. And 8 is one of those square roots you can simplify. Square root of 8 is the square root of 4 times the square root of 2. And the square root of 4 is 2. So this is 2 square root 2. Okay, so 2 square root 2 over 3, we got plus minus. We have to figure out which sign it is. So for beta, we have all students talk constantly. Beta is in quadrant 3. In quadrant 3, only tangent is positive, and so that means that cos is negative, which we knew, and also sine is going to be negative. So sine is negative. Okay, so now I'm going to go back to my formulas, and I'm going to write down the formula for sine of alpha plus beta. You can get it from the beginning of these notes, or you can go back to your resource page. So sine of alpha plus beta is the top symbol. So sine alpha cos beta plus cos alpha sine beta. Okay, and then what we're going to do is we're going to take these different fractions that we found, we're going to plug them in. So sine alpha is negative 3/5, cos beta is negative 1/3, cos alpha is positive 4/5, sine beta is negative 2 root 2/3, okay, so negative 3 times negative 1 is positive 3. 5 times 3 is 15. 4 times negative 2 is negative 8 square root 2. 5 times 3 is 15. So we have 3 minus 8 root 2 over 15 is our answer. All right, we have one more problem with these before we move on to some proofs. So this section helps us discover some more identities, and these are called the co-function identities. But to find them, we're just going to use a difference formula. So it says use the difference identity to find cos of pi halves minus beta. So cos, and we're doing subtraction here, so cos of pi halves minus beta is going to be cos of pi halves cos beta, and then plus sine pi halves sine beta. Okay, so I just went ahead and used this as the first angle, this is the second angle, and then I just went ahead and plugged them in. Cos of pi halves is 0 and sine of pi halves is 1. So I have 0 times cos beta plus 1 times sine beta, and 0 times anything is just 0. And then 1 times anything is itself, so I just get sine beta. So cos of pi halves minus beta is just sine beta. And that's this one right here. This is sine of this angle, theta in this case. They used a different variable. And all of these different identities can be proved using these difference identities over here. These you'd have to do some reciprocals and do a little bit more work. But all of these identities can be proved in a similar fashion. All right, so now let's go ahead and move on to the proof portion of the notes. Okay, so the strategy whenever you have sum or difference identities in a proof that you're trying to verify is to look at the two pieces of the proof. I can see that there's a sum identity right here, and typically you want to do a trig substitution for the sum or difference identity first, and then go from there. That has usually been the most beneficial for me. There are a few very unique cases where that has not been helpful, but generally speaking, that's going to work the best. So for these last couple problems, I'm going to go ahead and use the formulas over here. You'll notice that I shorthanded them, where instead of writing sine sum and sine difference as two different formulas, I put them together. So since the plus is on top, it goes with the plus that's on top over here. The minus is on bottom, the minus is on bottom. This one with cos, the plus is on top and the minus is on top, and that's because when cos has a sum, the formula has a subtract sign. And when it is a difference identity, when there's a minus here, it's actually a plus over here. So you just know which sign to use based on which sign's on the top or on the bottom. Same with tan, there's a plus on top, and on the top of the fraction it's a plus, but on the bottom of the fraction it's a minus. So you just go with wherever the symbol is. Okay, so this one says sine of alpha plus beta, and so I'm going to take this and I'm going to write down that formula. I'm going to do that substitution first thing. So for the top of this fraction, it's going to be sine alpha cos beta and plus, because that's on the top, cos alpha sine beta divided by that denominator, cos alpha cos beta. Okay. And one thing that you can do whenever you have two terms here with a common denominator is you can split these apart into two different terms, which is going to be helpful because on the right side we do have two different terms. So I'm going to split these. I'm going to write sine alpha cos beta with the denominator, and then cos alpha sine beta with the denominator. And then if I look at this, I can see that I can reduce this. So cos beta divided by cos beta, cos alpha divided by cos alpha. And so over here I have sine alpha over cos alpha, which gives me tan alpha. And this is sine beta over cos beta, which is tan beta. And so I've proved it. All right. For the next one, we have a sum identity and a difference identity on the left side, and then just something else on the right side. And so I'm going to go ahead and work on the left side, and I'm just going to take each of these identities and I'm going to substitute them out for what their actual formulas are. So sine of alpha plus beta is sine alpha cos beta plus cos alpha sine beta. Okay, so that's substituted out for the first one. And then alpha minus beta, I'm going to write sine alpha cos beta minus cos alpha sine beta. And that's the second one. And this is going to equal the right side of the equation. Okay? And what I'll see is that this term right here, cos alpha sine beta and cos alpha sine beta, that these terms are identical, but one is positive and one is negative. And so these are going to cancel each other out. And then over here, these are identical as well. Sine alpha cos beta, sine alpha cos beta, but they're both positive. So I have two of them. So 2 sine alpha cos beta is equal to 2 sine alpha cos beta. So those were some pretty simple proofs.